This is SpaceTime, Series 20, Episode 14, for broadcast on the 22nd of February 2017. SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe. You can download SpaceTime as a free twice-weekly podcast just about everywhere, including iTunes, Stitcher, Pocket Casts, Bytes.com, YouTube, SoundCloud, Audio Boom, and from spacetimewithstuartgary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C. Coming up on SpaceTime, discovery of a white dwarf pulsar, plans to change the Juno spacecraft's orbit around Jupiter dropped, and the first Dragon blasts off from the historic former Space Shuttle and Saturn V Apollo launch pad. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers have discovered their first white dwarf pulsar. A report in the journal Nature Astronomy claims white dwarf pulsars are a stellar class that's been speculated about for over half a century, but had never previously been detected. Up until now, all pulsars have been rapidly rotating neutron stars, the super-dense stellar corpses of stars much more massive than the Sun, which have exploded as core collapse supernovae at the end of their lives as normal main sequence stars. As they spin, pulsars release streams of energy, shining as bright as lighthouse beams. White dwarfs are also stellar corpses, but they're the remains of less massive, more sun-like stars, which have puffed off their outer layers at the end of their lives, exposing their white-hot stellar cores. The newly discovered exotic star, named AR Scorpii, was discovered 380 light-years away in the constellation Scorpius, a binary system containing a white dwarf and a spectral Type M red dwarf star orbiting each other. The study's authors, Professor Tom Marsh and Boris Jansky from the University of Warwick, and Dr. David Buckley from the South African Astronomical Observatory, detected the strange system thanks to the white dwarf's intense plasma and radiation beam, which was lashing its binary partner, causing the system to brighten and fade dramatically twice every 2 minutes. The authors found that the energy from AR Scorpii is a focused beam, emitting concentrated radiation in a single direction much like a particle accelerator, something which is totally unique in the known universe. The white dwarf in AR Scorpii is about the same size as planet Earth, but it's about 200 times more massive, and is in a 3.6-hour orbit with a cool red dwarf star about a third the Sun's mass. With an electromagnetic field some 100 million times more powerful than the Earth, and spinning on a period just shy of 2 minutes, AR Scorpii produces lighthouse-like beams of radiation and particles which lash across the face of the red dwarf. This powerful lighthouse effect accelerates the electrons in the atmosphere of the red dwarf to close to the speed of light. That's an effect never before observed in similar types of binary systems. The red dwarf is thus being powered by the kinetic energy of its spinning neighbour. The distance between the two stars in this binary system is just 1.4 million kilometres, roughly 3 times the distance between the Earth and the Moon. Marsh says the data shows that AR Scorpii's light is highly polarised. That means the magnetic field controls the emissions of the entire system. He says that makes it a dead ringer for more similar types of behaviour, usually seen in more traditional neutron star pulsars. Put simply, AR Scorpii's acting as a gigantic dynamo, a magnet the size of the Earth, with a field that is some 10,000 times stronger than any field scientists can produce in a laboratory. And all of this is rotating every 2 minutes, generating an enormous electrical current in the companion star, which then produces the variations in the light scientists are detecting. This is SpaceTime. I'm Stuart Gary. An experimental Japanese mission to help clear space junk from low Earth orbit has failed. The plan involved using a 700-metre-long electrodynamic tether to slow bits of space junk down just enough to cause it to lose altitude and begin the process of re-entering Earth's atmosphere. The device, made from strands of aluminum and stainless steel, was to deploy from the Japanese HTV-6 cargo ship after it undocked from the International Space Station last month. The Japanese Aerospace Exploration Agency JAXA claims the tether appears to have failed to deploy properly. The HTV supply ship had launched to the orbiting outpost in December last year aboard an H-2A rocket from the Tanegashima spaceport in southern Japan. Over 100 million bits of space junk are currently estimated to be orbiting the Earth. These range from giant satellites and even larger spent rocket boosters through to lost space tools and bits of debris from both accidental and deliberate orbital collisions. Currently circling the planet at speeds of 28,000 kilometers per hour, they pose a significant threat to spacecraft and crew. In the past, items as small as paint flecks have hit spacecraft, causing significant damage. Although small, a tiny fleck of paint travelling at over 28,000 kilometers per hour can quite literally punch a hole in a spacecraft like a bullet through butter. In fact, NASA space shuttles have occasionally returned to Earth sporting damage from just such collisions. Scientists wanted to test whether this tether idea could slow down orbiting space junk. However, failure to deploy meant the mission was eventually scrapped. JAXA managers spent a week trying to resolve the problem. You see, that's all the time they had before the HTV had to re-enter the Earth's atmosphere itself. Meanwhile, the Australian National University has won Australian Research Council funding for its own project to help clean up space junk. Associate Professor Celine d'Orgville from the Australian National University's Advanced Instrumentation and Technology Centre at the Mount Stromlo Observatory will use the funds to develop a new laser system which will be used to track orbiting space junk. The system will also allow telescopes equipped with adaptive optics to better measure turbulence in the Earth's atmosphere by generating a laser guide star. The laser guide star system will be crucial for both civil and defence telescopes, such as the new Giant Magellan telescope now under construction in Chile. D'Orgville says ground-based telescopes used to study the universe, image satellites or track space debris all require laser guide star adaptive optics in order to defeat the blurring caused by atmospheric turbulence. She says the semiconductor guide star laser will be a key component of these systems.
The first reason we got into doing adaptive optics is to help astronomers get better images at the focal plane of their ground-based telescopes. The reason why we need adaptive optics is because the light coming from the stars is going through the atmosphere, the Earth's atmosphere, before it reaches the telescope, and it gets blurred by it. So you need to somehow measure that blurring and apply correction so that you can correct in real time and get good images for astronomers to work with.
Yeah, twinkling stars are lovely for romantics, but they're not good for astronomy and science.
That's right. Astronomers don't really like the twinkle.
How does adaptive optics work? How does it turn a ground-based telescope? I mean, that's why they put telescopes on mountaintops, to try and get rid of as much of the atmosphere as they can. But exactly what does adaptive optics do to further supplement that?
Okay, so the basic principles to do adaptive optics is to use what's called a deformable mirror, which is a very flexible piece of metal or some other technology similar to it that we use to change the shape of the mirror in real time. So what we do is we measure the atmospheric turbulence and we compute what shape we have to give this mirror so that it can correct for the light deformation. We bounce the light off that mirror, and after it has bounced, it is flattened. We're talking about waves here. You know, the light can be described in terms of photons or waves. So if you think of it in terms of wave, when the light comes from above the atmosphere, it's flat. It's a flat wavefront, and when it goes through the atmosphere, it gets all distorted like a potato shape, really. And so that mirror, that deformable mirror, takes the opposite shape and corrects for that deformation when the light bounces off it.
And that must take an awful lot of computing power to do that, to constantly change the mirror to maintain the right optics regardless of the atmosphere.
We have to go very fast if we want to follow the turbulence. So typically, adaptive optics systems run at about 1 kilohertz, which is once every millisecond.
And I guess one of the important things is actually how you measure that turbulence in the air. And this is where I guess it's an artificial star, really?
Yes. So if you were observing an object like a star which is very bright, you can use the light coming from that object to do your measurement of the atmospheric turbulence. However, astronomers typically are not very interested in bright objects. They know them very well already. They want to see faint stuff, and there's not enough light to work with. So you have to create an artificial reference source, an artificial star, next to the object you're observing in the same direction, and you use that light to do the measurement for the adaptive optics to work. That's what I do. I create laser guide stars, so using lasers to create that reference source for the adaptive optics.
What does the laser bounce off to give you that artificial star? Is it just part of the ionosphere or something? Or?
Well, the way we do this is we use a layer of sodium atoms that is located about 100 kilometers above the ground in the mesosphere. And what we do is we use a laser that is able to excite those sodium atoms. So there's a special color that the laser has to have. It's called the wavelength, which is bright orange. It's basically the same color that you see in street lamps. You know those bright orange street lamps? They're sodium lamps. Mm-hmm. So there are sodium atoms in there. We do the same thing, except we use those sodium atoms which are high up in the atmosphere at about 100 kilometers up there. And we use the laser to excite them. And when they're excited, they glow. And that's how we create our star.
And that's your artificial star.
Yeah.
What sort of things can adaptive optics be used for? It's not just looking at distant stars. These lasers, there are also other applications for it, aren't there? And that's all part of the grant that you guys have.
Yes. So as I said, we started doing adaptive optics for astronomy, but now we're also doing adaptive optics for other projects. And one important project we're working on here in Canberra is this Space Environment Research Center that the ANU is part of with other industry and academic partners. The idea is to try to mitigate the problem of space debris. So you must know that by now we've sent so much stuff in space that there's a lot of junk orbiting the Earth. And really people at the beginning kept sending, satellites, and those satellites would die and just stay up there. And now there's just so many things, so many debris, that there's a big risk of collisions between debris and working satellites, or between debris and debris. And the risk is that there's going to be one collision and then another collision, and then to having more and more collisions, you create more and more debris, and then there's an amplification effect. It's called the Kessler syndrome. And what happens is that at some point there's going to be so many debris in space that you won't be able to send anything anymore, because the risk of colliding with debris will be too high. You won't be able to send manned mission, that's for sure. Probably it won't be possible to operate those satellites anymore because they will be damaged by collisions with debris. So it's a pretty catastrophic scenario, which, is actually realistic, and we need to do something about it. So the reason we use adaptive optics in this area is to send another laser, not the laser guide star laser, another laser in the infrared up towards the debris and illuminate them so that we can track them from the ground. And if we want to do a good job at sending that big infrared laser to the debris, we need to shape the laser beam as it's going through the atmosphere. For the same reason we do it in astronomy, is because the atmosphere is distorting the laser beam. So we use adaptive optics to do that.
The idea is to use these lasers to literally mark and track objects that are already up there and keep an eye on where they are.
Yes. You basically bounce some light off them. A little bit of that light comes back towards the telescope, and because you know where you're pointing and you can measure the time it has taken for the light to go there and back, you know exactly where the debris is. And from there, you can predict where it's going to be. You can calculate its orbit.
By keeping track of it, you can see which way it's going, what it's going to do. Was it,
right,
from a scientific point of view, was it very frustrating when, well, the one that always got me was when China blew up a disused Chinese weather satellite, simply to show the world they could do that. Was that something which frustrated you guys? Because it literally put thousands, if not hundreds of thousands more bits of space junk up there.
Yes, that was quite an unfortunate decision. So I think by now they have realized that was a big mistake and probably won't do it again. But, we always talk about the Chinese doing that, and that was bad. But I think other people have done it too, and they just kept quiet about it.
Okay, it's interesting. The problem with space junk, it's not going to go away for a long time. There are half a dozen different proposals out there now to try and remove space junk. Most spacefaring countries have already signed a document which will limit the life cycle of spacecraft once they're in orbit. In other words, they have to have enough propellant to either be placed in a geostationary position where they can't cause a problem, or they have to be able to be maneuvered so they re-enter the Earth's atmosphere.
That's right.
Is that one way of solving the issue, or at least remediating it?
Oh, well, certainly completely necessary necessary to do this in the long term. Otherwise, the number of debris will just increase too fast and we won't be able to manage it. But we still need to do something about the debris that's already up there. There's already too many of them. So there are, as you said, a number of projects that are proposed to either go in space and fetch those debris with some sort of gigantic net, or shoot them with another laser to modify their orbit and provoke them to re-enter the atmosphere and burn there. There's a number of other proposals. Our work at the Space Environment Research Center it's to demonstrate that we can first know where they are, predict where they're going to be, predict if there's going to be a collision, and then in case there's a collision predicted, instead of asking, say, the satellite operator to move their satellite out of the way, we would like to move the debris itself and modify its orbit just enough so that there won't be a collision. And to do that, we'll use just a slightly more powerful laser to slightly nudge the debris out of its current orbit.
That's Associate Professor Cillian d'Orgville from the Australian National University. And this is SpaceTime. I'm Stuart Gary. Okay, let's take a break from the show and talk about one of our sponsors. Audible's offering a free audiobook download with a 30-day trial to give you an opportunity to check out their service. Audible have over 180,000 different titles to choose from, such as Contact by Carl Sagan or A Brief History in Time by Stephen Hawking. Others include the unabridged version of The Hobbit by R.R. Tolkien, Divergent by Veronica Roth, and Born to Run by Bruce Springsteen. So many great books no matter what your taste. Over 180,000 titles to choose from. To download your free audiobook today, go to audibletrial.com/spacetime. That's audibletrial.com/spacetime for your free audiobook. Or you can click on the link at spacetimewithstuartgary.com. And now, back to our show. NASA's Juno mission will now remain in its existing 53 Earth day orbit around the planet Jupiter, rather than moving to a lower 14 Earth day orbit as planned. The decision follows problems with 2 helium check valves on the spacecraft's main propulsion system. Helium's used to pressurize the rocket's propulsion system when the engine's fired. This should happen within seconds, almost instantaneously, but the valves took several minutes to operate during a recent rocket burn in October, raising concerns. Juno achieved orbit insertion around the gas giant in July 2016. Its highly elongated and flattened 53 Earth day orbit is designed to allow the probe to avoid the worst of Jupiter's intense radiation belts. This extreme radiation is easily strong enough to destroy the spacecraft's delicate instruments. To help protect the spacecraft from this extreme radiation, much of the probe's key electronics are housed in a special radiation-resistant safe. But even the strong box can only provide so much protection when it comes to radiation resistance. So, Juno is on a special 53 Earth day radiation avoidance orbit. Even so, mission managers expect the radiation will eventually destroy the spacecraft. NASA says the 53 Earth day orbit will still allow Juno to accomplish its science goals, while avoiding the risk of a previously planned engine firing that would have reduced the spacecraft's orbital period to just 14 Earth days. Mission managers say, other than the sticky valves, Juno is healthy, its science instruments are fully operational, and the data and images they've received are nothing short of amazing. Juno has successfully orbited Jupiter 4 times since arriving at the gas giant. Its most recent orbit was completed on February the 2nd, and its next close flyby of Jupiter will be on March 27. Mission managers say the orbital period does not affect the quality of the science being collected by Juno on each flyby. That's because the altitude over Jupiter will be the same at the time of each closest approach. In fact, the longer orbit provides new opportunities that allow further exploration of the far reaches of space dominated by Jupiter's magnetic field, thereby increasing the value of Juno's research. During each orbit, Juno soars down to just 4,100 kilometres above the planet's swirling cloud tops. During these flybys, Juno probes beneath the obscuring cloud cover, studying the planet's auroras, atmosphere, gravity and magnetosphere, in order to learn more about the planet's structure, composition and origins. The original Juno flight plan envisioned the spacecraft looping around Jupiter twice in 53-day orbits, then reducing its orbital period to 14 days for the remainder of the mission, allowing more close encounters. However, a review by mission managers looking at multiple possible scenarios that could place Juno in a shorter period orbit found multiple serious concerns that another main engine burn could result in a less than desirable orbit which could impact the rest of the mission. Putting a positive spin on the story, NASA says Juno's larger 53 Earth day orbit allows for bonus science that wasn't part of the original mission design. Juno will further explore the far reaches of the Jovian magnetosphere, the region of space dominated by Jupiter's magnetic field. Included in that study will be the far magnetotail, the southern magnetosphere, and the magnetospheric boundary region known as the magnetopause. Understanding magnetospheres and how they interact with the solar wind from the Sun is a key scientific goal of NASA's Heliophysics Science Division. Juno's principal investigator, Scott Bolton from the Southwest Research Institute in San Antonio, Texas, says other key advantages of the longer orbit are that Juno will spend less time within the strong radiation belts on each orbit. That's significant because radiation has always been the main life-limiting factor for the Juno mission. NASA says Juno will continue to operate within the current budget plan through to July 2018. That will allow a total of 12 scientific orbits. The team can then propose to extend the mission during the next science review cycle. This review process evaluates proposed mission extensions on the merit and value of previous and anticipated scientific returns. Meanwhile, the Juno Science team are continuing to analyse their returns from previous Jovian flybys. Revelations include that Jupiter's magnetic fields and aurora are much bigger and more powerful than originally thought. Scientists also found that the belts and zones that give the gas giant's cloud tops their distinctive look extend far deeper into the planet's interior than previously imagined. Peer-reviewed papers with more in-depth scientific results from Juno's first 3 flybys are expected to be published within the next few months. Bolton says Juno is providing spectacular results, rewriting science's ideas of how giant planets work. This is SpaceTime. I'm Stuart Gary. A SpaceX Falcon 9 rocket has made history, blasting off from Launch Complex 39A at the Kennedy Space Center in Florida. That's the same launch pad previously used by the mighty Saturn V Apollo moon rocket and more recently by the Space Shuttle fleet. SpaceX are leasing the historic launch complex at the Cape Canaveral Air Force Station in Florida from NASA. The facility will eventually also be used to fly the Falcon Heavy, SpaceX's new heavy lift launcher, as well as the Dragon V2 capsules designed to carry crews to the International Space Station. For this inaugural launch, the Falcon 9 was carrying CSR-10, the 10th Dragon supply mission to the International Space Station.
T-minus 20. Falcon 9 is configured for flight. T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Liftoff.
And Falcon 9 is on its way to delivering Dragon for its 10th commercial release resupply services mission. This is the first time a launch vehicle has left Earth from 39A since the Space Shuttle Atlantis in 2011. Everything continues to proceed nominally. We are just about to transition through max Q, maximum aerodynamic pressure. It's right after we trend past supersonic. Max Q is one of the highest stress states on the rocket. Right after this, we're going to be proceeding into kicking over for our inertial pitch. That's where Dragon is going to start going on an orbital trajectory. Everything continuing to look nominally for today's launch. We have main engine cutoff, stage separation, and we have a second stage engine start. The first stage is on its way back for its first maneuver burn. It will have a 3-burn process, the entry burn coming up, or the boost back burn, sorry. Meanwhile, the second stage is continuing to perform nominally. It's got a 6-minute burn. The first stage burn continuing to proceed nominally. This boost back burn will go on for about another 10 seconds.
We had a successful main engine cutoff, a successful stage separation, and then a successful second engine start. It was a little cloudy for the Falcon 9 coming off the pad, so we didn't get a great view of it.
I don't know about you, but I got chills seeing the booster fall away from from the engine and just kind of glide back towards Earth and rotating like a great shot.
Now, there are 3 different
burns to get back to landing zone 1. There's the boost back burn, which successfully completed. Then there's the re-entry burn, which is to slow us down as we go back through the atmosphere. And then there's the ever-exciting landing burn as we approach landing zone 1.
The grid fins on the first stage pop out right there. We use those to dynamically steer the vehicle as it comes back down using air resistance as it passes through supersonic airstreams to get it back towards the landing zone 1 at Cape Canaveral.
Primary mission is still going well. Dragon on top of second stage, making its way to the International Space Station.
A quick note about those grid fins. People always ask us, how do they exert such large force on such a large cylindrical body? And it's the same principle. If you stick your hand outside of a car when you're going 10 miles per hour on neighborhood streets, it doesn't affect you very much. But if you stick your hand outside when you're going 80 miles per hour on the freeway, you can exert a very, very large force upon a large surface simply from the air particles. The grid fins are doing the exact same thing. They're little airplane wings that are steering us back to landing zone 1.
Yeah, so just in case if you're joining us right now, we had a cloudy but successful liftoff of Falcon 9 from Launch Pad 39A at Kennedy Space Center in Florida.
We have the grid fins, which act as wings of it. We also have nitrogen, and we have cold gas, and we spew those to exert small forces to help us laterally as well.
About 6 minutes into the count right now, everything continuing to proceed, and nominally your first stage is guiding back to Earth. It's coming up for its entry burn. It's the second of the 3 burns. That entry burn should kick in about 15 seconds, 15 or 20 seconds from now. We just deployed the grid fins. That means we're coming back into the atmosphere, and we'll use those for coming back to Earth. That call out was confirmation that the ignition did just occur. This burn itself is going to last for about 15 seconds, and it has just shut down. Looks to be good right there. And then we have a landing burn coming up in about a minute from now. That landing burn lasting just to touchdown for about 30 seconds. The stage 2 burn is going to last for about another 2 minutes. Continues to perform very well. That stage 2 engine has pretty deep throttle capability. It can go from about 81,000 pounds to 210,000 pounds. That's how we target that precision orbit. We put in a parking orbit of 200 by 600 kilometers. Meanwhile, stage 1 is transonic right now, transitioning through the speed of sound as it's coming back to Earth, and everything is looking good to go.
It was cloudy on takeoff, so we are expecting some clouds as we re-enter.
It is approaching the landing zone now.
Landing
We're seeing
lights
on the
out.
screen. Touches down successfully on LZ1. Congratulations, Falcon.
The Falcon has landed once again, landing zone 1 in.
So it looks like the clouds are just beginning to break there, making for a pretty picture-perfect landing. No video from the ground like we had expected earlier, but we did get great video all the way down. So right now, the second stage looks like it's also proceeding normally. The primary mission today is, of course, to bring the Dragon to the International Space Station, and by all accounts, it looks like it's going very well right now.
Yeah, so over the next few moments, what's going to come up, second stage is still attached to Dragon, so they're going to continue for a moment. Dragon will deploy its nose cone, that aerodynamic shield that it keeps to move through air efficiently. It will deploy that because once it's out in space, it doesn't need that mass. Then eventually Dragon will separate from second stage and will continue on its phasing up to the International Space Station.
Exactly. During that time, we will also see things like the deployment of the solar arrays from the trunk section, which Brian mentioned earlier in our webcast, that is the unpressurized section of the Dragon capsule.
Now, the Dragon doesn't just go straight to the International Space Station. It actually slowly approaches over a series of days.
The Dragon's delivering some 2.5 tons of scientific equipment and supplies to the orbiting outpost, which will support dozens of the more than 250 science and research studies now being carried out during Expeditions 50 and 51. Included in the cargo manifest is the Stratospheric Aerosol and Gas Experiment, or SAGE-3 instrument. It's designed to study levels of ozone, aerosols, nitrogen dioxide and water vapour in the stratosphere and troposphere high above the Earth. It's the latest version of an experiment which began in 1979 and has created a multi-decade record of measurements. The new instrument will be connected to the outside of the station, making daily observations of the planet for several years. Another instrument, the new lightning imaging sensor, will replace an earlier instrument recording the time, energy output and location of lightning events around the globe. Because lightning's both a factor and a gauge for a number of atmospheric processes, NASA as well as other agencies will use the new LIS lightning data for applications from weather forecasting and climate modelling to air quality studies. The total and spectral solar irradiance sensor will measure the total solar irradiance and spectral solar irradiance, in other words, the total amount of energy from the sun that reaches the Earth's atmosphere. It'll also monitor the spectral distribution of that solar radiation, all critical for climate modelling and atmospheric studies. Another experiment will be growing plants aboard the space station which could provide food for future manned missions to Mars. Other experiments aboard the Dragon include a crystal growth experiment designed to crystallise a mitochondrial antibody that's undergoing clinical trials for the treatment of immunological diseases. Better defining how some bacteria become drug resistant is the focus of another experiment, this one aiming to develop new medicines designed to counter superbug resistance. Stem cells like those used to treat strokes and other diseases will also be studied using experimental supplies brought up on this flight. Dragon's due to dock with the space station later today. It's scheduled to remain there until March, before returning some 2 tons of supplies, scientific hardware and crew equipment back to the ground. The first ever launch from the Kennedy Space Centre's Pad 39A was the Apollo 4 mission on November 9, 1967. That was the first test flight of the mighty Saturn V rocket, which eventually took Apollo astronauts to the Moon. The first space shuttle also lifted off from Pad 39A. That was on April 2, 1981, when the Space Shuttle Columbia blasted off on STS-1. And on July 8, 2011, the very last Space Shuttle mission, Atlantis on STS-135, also launched from Pad 39A, bringing the Space Shuttle era to a somewhat premature end. Launch Complex 39A has an identical twin sister, 39B. That's also in the process of being modified for a new life. It'll launch NASA's new heavy lift rocket, the SLS, which will take astronauts aboard the Orion capsule on deep space missions beyond Earth orbit. I'm Stuart Gary. This is SpaceTime. And that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, and from spacetimewithstuartgary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C.
This is SpaceTime with Stuart Gary. For more, you can follow us on Facebook, Twitter, and Tumblr. Just search for SpaceTime with Stuart Gary.
SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.